So guys in the back, can you hear me? There, can you hear me? No, if you're
quite loud. I'll be really angry.
Someone is in the computer, they can't hear me.
Yeah.
That's probably why. My name is Taivo. I flew in today from Tallinn. I'm Estonian and I work at Veriff. My talk today will be about what we have been able to achieve in the past 1 year in the rough area of machine learning at Veriff. Okay. Is this good enough? Yeah. I have to train my lungs at home for the next talks. So can I do a quick poll? Raise your hand if you have ever written more than 10,000 lines of code. So total over your life. Raise your hand. Something like 85%? Okay. Raise your hand if you self-identify as a software engineer. Okay. Data scientist? Okay. Product owner, product manager, analyst, something like that. One, two, 1.5. Everyone else, can you shout out what you do? We got the 100% coverage, or it's the. I mean, like Estonia is supposed to be more north, and we're supposed to be like the more reserved ones. But I think this crowd here is very Estonian. Finnish people, okay. Northern Finnish probably, yes. First let me tell you about my background. I got my degree in computer science from Switzerland, ETH Zürich. I worked at a few Estonian startups for a relatively short while, doing data analytics and a little bit of predictive modeling at Skype and TrustWise. And the thing I did before Veriff was I was working at Starship on self-driving software for the Starship robots. The main sort of impact or goal was for the small robot that delivers packages, me and the team I was part of, we had to build software that, based on sensory input, understands where the obstacles are, where the cars are, people are, etc. around the robot. And today at Veriff, my main, my official role is automation lead, which is kind of intentionally is not the standard thing, so it says almost nothing. Very few bits of information you get from that. And what I am responsible for are the teams that automate the human activity behind our core product. And I will get to that in a second. Our product, imagine that you want to rent a car. You know, you want to travel to Iceland, you want to rent a car. For the car rental company to make the onboarding process or the rental process as fast as possible for you, they ask you to verify your driver's license remotely, online. What they do is they send a request to Veriff. Veriff shows you our end user flow, and this is what it looks like. You pick which document to use. You would choose driver's license. Take a picture of your face, of the front of your document, back of your document, yourself with the document, and that's it from your side. From Veriff, a response goes back out to the car rental company, and then they can choose to do whatever they want with it. The company itself was established almost exactly 4 years ago. We went through Y Combinator, which is one of the top startup accelerators in the world. That was about 2 years ago. And we've been funded a total of 8 million. And we've grown, when I joined a bit more than a year ago, I think we were at 35 people. So basically 10x in a year, which is amazing, but also horrible. This is a whole other talk. So automation at Veriff, this is my area or my team. Let me explain what we do. Fundamentally, I'm building a decision-making machine. We get in photos, the photos that I just showed you that the end user has to take, and the video in some cases. We have to give out a response. Is this person who they claim to be? That means, does the person match the document? Is the document a valid one? Does everything look non-suspicious, let's say? And what is the, let's say, the data written on the document? The first name, last name, birth date, issue date, gender, etc. So it's relatively well defined, the task we have to solve. the approach we take, we as a company, is we combine algorithms and humans to do both, or to solve this task. And the reason, there are many competitors of ours who use either algorithms or humans, but the reason you have to use both is that they have basically complementary strengths and weaknesses. So what algorithms are great at, algorithms are fast. You know, even the heaviest image processing algorithms you can probably run within 1 second if you take the right compute unit. Humans are super slow. It takes you like 5 seconds to switch context from one image or one document to the next. Algorithms are scalable. You can easily scale out, just add machines on Amazon. Humans are in principle scalable, but it's much more difficult. The lead time is, takes you 2 months to hire someone. I guess it's also more expensive. And from some point onwards, it is not feasible. Like, you probably wouldn't be able to hire 10,000 people every month. Algorithms are easy to modify. So if we figure out that we need to change our product, the decision-making machine in some way, then, changing an algorithm is one change in code, commit straight to master, deploy to production, obviously. And changing the human's behavior, it takes training. You can do it in, let's say, days, weeks, but still there's a significant lead time. And with algorithms, you can have infinite nuance. So there's like 3,000 documents, 3,000 different kinds of documents that are available globally. And there are many exceptions we need to make when processing these. For any single human, let alone for hundreds of thousands of humans, to remember all of these exceptions, it is pretty difficult. And versus algorithms where you can just literally write them in code or in a database. On the other hand, humans are literally the definition of perfection for an algorithm, or not quite, but more or less. So human level is the target. Humans onboard fast. So when we hire an operations specialist, it takes them a few days to a few weeks to get productive, let's say, depending on what exactly they do. Versus, when we start building an algorithm, to the time when it is valuable in production could take months, or in the most difficult cases, up to a year. Algorithms make stupid mistakes. So humans have common sense. For example, if you have some sort of first name extraction and you accidentally extract from the wrong place in the document, you extract from the place that says Republic of Estonia, then no human would plausibly consider this as someone's first name. But an algorithm, unless you explicitly check for it, will probably not be able to sort of figure this out. And humans generalize very easily. So when I show, let's say, most of you probably haven't seen a Swedish ID, for example. But if I show you one, you'll probably figure out, where the data locations are, where the photo is, what the holograms more or less look like. You have some sort of intuitive feel for the simplest fakes. So, and algorithms, in contrast, you need to either explicitly program them in a particular way, or you need to train them on, Swedish ID cards for them to work well. So this is the context, or this is basically what we're building, a combination of algorithm and human decision-making machine. And I think additionally, the context for us is, for the automation team inside the larger engineering organization, is each request is very high value. So for a payment API like Stripe, for example, each request is relatively low in the amount of compute you put into it. It costs relatively little, versus verification, which costs a relatively large amount, and it is valuable for the customers because the downside risk if something goes wrong is potentially pretty bad. They might lose their license if they're not compliant. In some cases, fraud costs quite a lot. So the value of each request and processing it to the maximum accuracy is very high. Second, a lot of what we do is kind of unpredictable. I summarize it as researchiness. So we are, for some tasks, I'd say like 20–30% of the work we do, it's really difficult to know what the value of a potential development would be, and also what the effort to get to that level would be. I guess these are kind of related, but the unpredictability is definitely part of the context. And also we have to collaborate a lot with an operations team, or actually we have several partners within Veriff, several teams, which help us build algorithms. So one kind of partner is we need to label a lot of data. We call it data annotation, and we have a special team for managing data annotation projects, and then we have a bunch of humans actually doing the data annotation. And QA, which is not QA in the sense of software testing, but it is QA in the statistical sense of looking at what our algorithms output, and then giving us a statistical summary of basically based on human judgment, how accurate the responses are. Something that I think we all share, we still have SLAs, we still have to have 99.99 whatever uptime. We still care about software quality, maintainability, security, etc. So all of these constraints are still there. So what do we build? Let me show off probably the pictures you've all been waiting for. So this is a face detection algorithm, production output from that algorithm or from that service. A relatively trivial one because face detection is more or less a solved problem, I would say. This is the input image. This is the output from that service. Gives the rectangular bounding box of the face here, and also a descriptor for the face, so we can compare it with other faces. Another example from the same image, we want to figure out what exact document this is. So we want to know that it is from Estonia, it is an ID card, but that is actually not enough because Estonia has 2 valid ID cards simultaneously. So one is the old one that is in this picture, and there's a new one which they started issuing this year. So we need to figure out which one exactly it is, because the layout is different, the security elements are different, etc. And some countries, when you talk about, for example, the US driver's license, it's not a single document. Every state has like 5 or 6 versions of driver's licenses, and they all look different. The worst part is many of them look very, very slightly different, but enough to make your algorithms bad. So we need to know exactly what we're dealing with here. And this is an example of production output. I'm showing the top 3 class predictions. This is the correct one with a very high confidence of 97%. Top 2 class is the second Estonian ID, and the third one is some Finnish one, which also looks relatively similar. This is another example. I think the coolest thing I can show you. I'll let you look at the video for a little bit. So what's happening here is, this is the input video. Here, this is a pipeline for basically figuring out where exactly the document is. Input video, pixel-wise classification of where do we believe the document is. So for each pixel, do we believe this pixel contains any of the document or not? This is basically these are 3 post-processing steps on top of this, with varying degrees of stability. So stabilization pipeline, and this is basically the final result. So even though the camera moves, we can get the relatively stable, in this case very stable image or video of the document itself. And what this helps us with is, once you have many frames of a single document, you can improve quality. You can read out the texts better, but also you can do things like hologram detection here, and the other things which I don't want to talk about. Fraud is like, the problem with me giving talks is, if I say what are all the things we do, it makes it easier to attack us. I know it's security through obscurity, but it's still security. So this is the previous ones were algorithms that I didn't show you how we apply them, but these are now features in the actual live product. So if you take a picture, you're told to take a picture of your face, of yourself, and you block your face, or your face is not in the image. We give you instant feedback that we can't see your face, please show your face. Same with, we tell you to show the back of your ID card, you show the front of your ID card, we tell you that you should show the the other side of your ID card. We have something like 10, 15, I don't know exactly how many, but a bunch of these checks and let's say recommendations for the end user for them to be more clear what they're doing wrong if they're doing something wrong. I'm sure if you have onboarded to Revolut or an N26 or something like that, you've had this experience where you complete the ID verification flow. You know, you're happy, you get it done. Like 2 hours later, you get the response that you need to do it again, and you go in the loop again for like 5 times. So this feature helps avoid that to some extent. We tell you if something is wrong immediately, not 2 hours later, or even 30 seconds later. Generally, let me arbitrarily divide our algorithm work into 3 classes. So in terms of like machine learningness, or how much, if you ask the random, let's say, developer on the street, is it machine learning? Then there's an axis. So software 1.0, it's not machine learning. Nothing is learned. You know, hard-coded if-else rules, database lookups, one-off annotations of what do we expect a specific document to look like. For example, what is the format of the Estonian ID code? 1.5 is this, I'm calling them hybrid algorithms here, which is like barely learning. Typically, these are algorithms with a few parameters that you can change. Could be a classical computer vision algorithm, could be some sort of out-of-the-box model, which you have to threshold somehow. Could be that you manually optimize some against the data, some piece of code that does not have any parameters in it. So this is kind of where you have this learning loop, where you build a solution, evaluate it numerically against the data for its performance, and then change the code and do it again. So these kinds of things where you could consider it like almost machine learning. And then there's actual, let's say, deep learning, which is the thing that people think is like, yes, this is the automation. This is what we do. We spend all of our days training deep learning models, and it's true. They form an important part of what we do. But we want to avoid training our own models as much as possible. So one way to do that is use a pre-trained model. Basically, someone on the internet has pre-trained a model, and we can just, if it is valuable to us, we can deploy it on our servers, or use an API from Amazon, Google, Azure, whatever. We can also, and like as the last resort, basically, we can train models in-house. Why it is the last resort is the amount of data that you need is relatively high. It is very unknown how much data you need to actually get to the performance you require. And whenever you go into like a even slightly non-standard task, it's not even clear that it is easily possible. Like it maybe takes you like 6 or 9 months for like one researcher to make that work. So this is the reason we do deep learning as little as possible. And if I assign like percentages of, I think this is more like time, not necessarily effort. Most of our time is spent in this layer. Some of our time also in here, and as little as possible here. However, I know 10% is very little. However, if you think about a car, no, I thought someone was raising their hand. If you think about a car, the engine weighs like approximately 10%, maybe 20% of the car weight, but it kind of doesn't make sense to have a car without an engine. It almost doesn't make sense. So in a similar way, we don't spend most of our time on deep learning, but without it, it would be very, very hard for us to build a car. And most of our time goes into actually building the chassis, the wheels, the interior, the body of the car. I thought it might be interesting to show you, these are actual tickets slightly edited that I took from Jira. So make one particular service that runs an algorithm, make it faster. This could mean, making let's say the image loading time into the service faster, but often it also means changing the algorithm itself, because sometimes the algorithm is written in an inefficient way, or it is efficient, but if you downscale the input, the quality will stay the same, but you get faster processing. So this is one example of an algorithm ticket. Second one, train the document classification model, which I showed you, train it on a new dataset. Investigate a particular algorithm for false positives for unstable images that are relatively shaky or blurry. Review the data annotation quality for a task. So if you want to build, let's say, build a blurriness detection model, and you want 100 examples of blurry versus not blurry images, then someone has to come up with the annotations. And as a data scientist, you're kind of responsible for making sure these are high quality annotations, because this is what goes into your development. Or build, one of the edge case exceptions for a particular document. What I showed here in this slide so this is just the algorithm work. We also have non-algorithm development, or I guess everything is an algorithm, but in my head, by algorithm I mean statistical algorithm, something we measure by its statistical performance, not with unit tests. So algorithms are only a part of what we do. We also have this bottom layer of almost any service you set up. We'll have to have some sort of storage, some sort of communication middleware. We have a microservice architecture, monitoring on top of that, all of these basics. This we also have to deal with. And on top there is, I would say, mostly machine learning related things, statistical testing. So we want to take 100,000 historical images for which we know what the correct answer is, and run the current newest algorithm or a proposed algorithm through these images to see what the performance of the algorithm is. Algorithm debugging tools. So the complexity or the amount of moving pieces inside our automation stack, it's big enough that it's not necessarily obvious where things go wrong. So for example, when we fail to extract any data from an image, it could be that we failed in the OCR failed. It didn't read out any text. The actual characters were not read out. Could be that we failed to find where the document is exactly placed in the image. Could be even that there is no document in the image, and we should have detected it in the end user flow that there is no document, and we should have forbidden the user to continue. So there are many, like getting to the bottom of this is not trivial, and we have tools for that. Annotation tools. So once you start looking into the open source and commercial software that allows you to label, let's say, tens or hundreds of thousands of images, it is lacking. So if you want to build something, come to me, and I say that in every talk, like I will be your first customer if you solve my data annotation problems. And the business logic, which is, I guess, a layer on top of the algorithms. So given that we detect some sort of discrepancy between, something is off, let's say, with the document, different customers or different businesses have different requirements for what to do with that problem. So this is also something we have to apply on top of this this output of our algorithms. And I hope you can see it way from the back. This is the deep learning part of what we build. So I spend so much time talking about this because most people have the wrong impression that deep learning is all you need, or that deep learning engineers are all you need. I'll get to the team composition slide later, and you will see what I mean. So this was basically the part about building algorithms and running them in production. There's also this part that does this communication and task assignment between humans, algorithms, and produces the final outputs. This is also something we're responsible for, but I won't go into detail with that. So data annotation, I think we have some interaction coming up here. You have all seen the demos or the blog posts about how neural networks can detect objects, right? Right, yes. Cat versus dog classification is a common example. Or in this case, the goal of the neural network is to detect the bounding box of the cat. So detect where the cat is. It's a relatively straightforward task. The way this is done, if you didn't have any public data for that, the way you would do this is you take a bunch of images of cats, you annotate them with ground truth. So what is the box that should be predicted? You train the model on top of this data, and then you get an artifact, put it into production, and hope that the predictions that it makes are good. The way I presented this right now is the way it works in, I think there's this machine learning guy who does YouTube videos. I think it works there, and it works in blog posts, but it doesn't work in real life. So what happens in real life, I want you to annotate images with me. So, where do we draw the ground truth boxes for this image? Where are the cats? This was a question. Where are the cats? Okay, let me give you
all over the place.
So who agrees that we should do something like this? This would be one cat. Yeah?
You cut his hair off.
Okay, let's say more or less like these 2 points, right? Here. Let's say, yeah. And this one would be like from here, right? And I guess almost up to the corner of the edge. Anything else?
These are not cats.
That is a good question. Like, I don't know if they are cats. I think these are toys, not cats. So this is the first question. Like, do you annotate toys that look like cats? There's a second question. These are reflections of the cats. Do you annotate these as well? Do you want to detect these as well? Like, are these cats, basically? Then there's a question of, let's say here, I think it's relatively clear what's happening, but if you didn't see behind it, if the skirt was not see-through, would you draw the box of the cat like here, or here, or up to the end of the image? All of this is unclear. So, yeah, this is just me highlighting some of the problems. Second example. What are the boxes of the cats? Or cat?
Small one.
Yes. Well, the small one, like this is on this one. How about the reflection there? Okay. But if you had to annotate the tiger class, what would you do? It's a reflection of a cat that is photoshopped into a tiger. Like, is it a cat?
You're going into semantics now.
Exactly, yes, I am. It gets worse. So the question here is, the main question here is, do I annotate only the visible part of the cat, or also the sort of implied part of the cat that you believe exists in the place where you cannot see? And this is, by the way, this is a practical problem. If you like replace cats with cars, in Starship's case, it is a very practical problem. Or in this case, it's kind of hard to even tell where the cat ends and the bed starts. So, you kind of have to guess. You have some sort of prior on what is the shape of a cat. Does anyone know the correct answer to all of these problems?
Depends on the business problem.
Yes! You let the product owner annotate the data. I'm not kidding, by the way. So there is no point in arguing over like the metaphysical definition of what the cat is, because it doesn't matter. What matters is what you want to detect, what is valuable for the product, or what is the product requirement. And basically you should take it as far as sitting down with the product owner and having them draw the boxes or doing it together and agreeing on what it means. Because fundamentally, if someone tells you detect cats in images, you will have to make these trade-offs for any like non-trivial real-world problem. And if this trade-off is made by you or as an engineer, the client will probably not be happy because no one took care of making sure that the output is what the client wanted versus what you thought were like metaphysically were the cats. So this is one thing, that annotation is a product problem, and engineering should provide tools and potentially also educate product. But products should basically define what is the task, and part of the definition of the task, I would say even the most important part, is how you annotate the data, because that becomes the specification of the problem. The two, or actually three main categories of data annotation is, one is this that we just talked about, where you sit down with a product owner, go over like 100 examples, and agree on what it should be like, or what the task is basically. But if you want to train a model, you need larger amounts of data. So let's say you want to do only cat detection, but you want to scale it to be very, very good. So the data set has to be relatively large, 10 to 100K examples. Then this is another sort of another context of annotation. And the third one is when you want not necessarily maximum count of annotations, but you want some balance in your classes. So let's say you want to detect all animals, and this means your training set should have at least a few examples, probably like 50, 100 or more, of each animal that you want to detect. There are also more delicate questions of balance. So in Starship's case, they operate in several cities in the US, the UK, Germany, Estonia, I think Finland to some extent as well. And if you only train your model on, for example, on the US, then the performance in Europe will be worse, because cars look slightly different and the roads look slightly different. So you have to take really good care that you balance your data set across all of these features. In Veriff's case, it could be that we want to balance ourselves across countries, across document types, across ages of people, across races of people. Basically, any dimension you can think of, you want to balance across that to get maximum performance. The question of, I up to now I explained mostly what we've been doing, but the how is, a good team. Today we have 7 people in data science, 7 people in software engineering, 3 people in data annotation. Like I said, this is only the management and tooling part. The actual labeling is done by, depending on time, like 10 to 50 people, somewhere either in our office or depending on data partners, and 2 product owners. Plus, in addition to that, we have a lot of partners inside the company, QA, the statistical QA, which I mentioned, DevOps, document research, which tries to create a comprehensive database of all documents that exist globally. This has not always been the case. In 2018, we started as the ML team. We were part of the general engineering pool, let's say, of like 9 developers, I think. Me and a friend, we joined together at the same day. It was a year and 7 days ago, I think. The reality was that he was doing the actual engineering, and I was like half-time PO, product owner, half-time recruiter. From, I think, like 3 or 4 weeks after I joined, I started doing like 5 to 10 interviews a week, because it was so clear that we need to grow extremely fast, that team. Early 2019, we rebranded ourselves to the automation team. We were now separate from the rest of the engineering, 7 data scientists and engineers, mostly data scientists. The reality was that we were not really independent. We needed significant support from other engineering teams, even for relatively basic things like setting up our own microservices, and mostly because we didn't have many software engineers in our team. And today we have several teams under the automation area, 2 product teams with their own POs, probably going to grow that in the very near future, 20 people total. And I mean, this is almost a reality that we have an independent roadmap, and consistently we can deliver on that roadmap. If you're starting to build, let's say, a data science or machine learning team, this is advice for you. Trying to find people with experience in data annotation. Like, what would be the job description? What would be the job role? What would be the previous experience you look for? Something like this hasn't really existed, I would say, and definitely not in Europe, or at least in the Baltics. I don't know of any other company that where I could hire from, except Starship. and the data annotation, one of the data annotation guys from Starship joined us pretty soon into the team history. Another thing, trying to find computer vision or machine learning engineers with more than literally 0 months or 0 days of practical, industry experience, it is difficult. Because first of all, there are very few of these people compared to the amount of people who are like, I'm a software engineer interested in, or I'm a student interested in, I'm a physicist interested in, etc. And somehow, I didn't really expect this, but it has been difficult to find senior backend engineers that are, by backend I mean not just like web app backend, but processing heavy loads of like images, videos, and building up, let's say, more complex backends than a typical web app would have, and who would be willing to, let's say, work with Python, because that's the de facto language of machine learning and data science. So my solution to all of these, or the first two at least, was to hire from my own network as much as possible. I think the first 9 people other than me in the team were from my network. And the second one, especially here, if you realize that there is no way you can overpay someone compared to DeepMind, for example, then the solution we took was hiring very talented people with strong programming and math backgrounds, and then kind of coaching them as much as possible and hoping they will figure things out. I think that's kind of the best you can do if you lack people with actual experience. And the third one, I mean, this is, our recruitment team has been working on this for 8 months, and I mean, if you have a good solution, let me know. Or if you want to apply, then my email is at the end. So just some thoughts for discussion. The impact that the team has had. Fortunately, it's very easy for me to go into our analytics tool and be like, then we count all of the decisions we made, which humans didn't have to do, multiply it with the price, and we have the financial impact of the team. That's not the only impact though. We also have impact on the whole product SLA. So how quickly we give out answers depends on how many sub decisions we can make automatically. We are able to serve new clients because the scale we can now do, and let's say the speed requirements we can fulfill are basically we can now do that. And we have built. There is one thing I think I'm most proud of is we came up with and built a completely new product that we offer sort of alongside our current product, and it is turning out to be very, in Estonian the phrase for that is hot bread. So it seems very valuable to the clients that we have talked to about this. And I think many of the engineering challenges that have remained or kind of are present throughout the past 1 year. One is, if you think about the, let's say, 20 core algorithms that we run, they form some sort of dependency graph. So the inputs are images, the output is the decision, and there's a dependency graph of different algorithms in between. There are 2 completely different execution modes for this compute graph. One is the production mode, where you want to get basically minimum latency. You want to get the answer as fast as possible. Doesn't matter if you waste like 80% of the GPU, for example. And then the second one is maximum throughput, where you want to do statistical testing, 100K images. You want to get the result in like relatively reasonable time, something like 10-20 minutes. And somehow, maybe I shouldn't be surprised, but there doesn't seem to be any out-of-the-box solution or any framework that offers very good support for both of these modes. Second one is handling all of the edge cases, all the 3,000 different documents, but also the different requirements from different clients, because many of our clients are large enterprises, and we want to deliver as custom product for them as possible. Third one, edge versus server inference. So once we have a model trained, or let's say our automation stack that makes decisions, ideally the latency would be minimal if we could run it on the end user's device. So that would be great. But there are problems with hardware support, security, what else? Many factors that they play into this. And ideally, I would see a hybrid model, but this is very hard to pull off. So this is a difficult engineering challenge. And the fourth one is how to make data scientists and software engineers work together productively, because the mindsets are very different. Data scientists are like, I want to solve 90% of the problem, and the rest of the 10%, I don't care if it's an exception. I don't care. Like I'll just do like with ignored, you know, any exception, do my thing. So the software quality push that comes from the software engineering side, it is like there is a strong counter push, let's say, from the practical, like problem solving data scientist side, who go for maximum accuracy and not necessarily maximum, let's say, maintainability or software quality. So that's it about talk. If you want to like follow different things I'm doing, this is my GitHub account. A comprehensive list, all of the talks I have given and will give is here in this repo. This is a very popular, I think, or for me at least, very popular repo, something like 100 stars. It has a list of all tools that I am aware of for data annotation. So image labeling, video labeling, text labeling, etc. This is a very unpopular repo, 0 stars. It has this kind of a pretty unclearly written, but on the other hand, I think promising list of data sets that, in principle, if you put it together, I think it would be relatively easy to do something cool with it and probably publish a paper on top of that. So the short pitch for that is, most people that publish papers are not willing to put the effort in to collect the data. They sit in an armchair, download the data set, and then like try to improve the model. Versus if you take like 1 month and €1,000 to put together a good data set and then publish some like extremely basic model on top of that, that I'm like 80% sure you could get a PhD in 1 year by doing 3 papers like that. I haven't tested it yet because I don't care that much about the PhD basically. And I also star a bunch of things, so I try to follow things relevant for computer vision and data annotation. If you follow my star feed, then you'll probably see like many of the coolest things popping up there as well. And this is my blog, which, like all blogs, I am sorry that I don't update more often. So this is my email if you want to reach out. Thank you very much.
So we have some 5, maybe a bit more minutes for questions. You have questions?
Yeah. That's a problem that all verification sessions are done automatically. Everything.
So the question is, are all verification sessions done automatically? Your question was, are all verifications done automatically?
Yes.
The answer, so first of all, the answer is no. This is not the model that we do. We do basically maximum quality and automate when it is possible to maintain that quality. So there are companies which are fully automatic, which offer you kind of a response when possible and kind of best effort response. But we offer like best overall effort together with what the human thinks response. That said, the actual automation rates depend heavily on which document it is, which device it is. Laptop cameras are much worse than phone cameras, for example. Sometimes depends on client as well, because Mintos, by the way, is one of our clients, and they have a very like, they have put in a lot of effort into building the best end user flow. So there, the incoming quality of images or of the sessions is very high. And this, compared to, let's say, if you were to randomly throw a link to the user, not explaining anything about what is going on, you would probably get a worse automation rate because the input is worse. So it heavily depends, and it's hard to give like a overall answer.
It's a slightly more abstract question about software engineering and data science. So one of the problems in working with problems like these, in regular software engineering, it is very easy to give your rough estimate to your product owner or product manager, how long it will take to complete the tasks, like 6 months to build a backend with some front end. But in more complex problems like these with data collection, data annotation, training neural networks, you can't really say with high confidence that they'll be done in 2 months. Sometimes it might take a year. How do you actually estimate things like these?
I was hoping you wouldn't end with a question, because then I would have said yes, and then that would have been it. So I had like 6 extra slides which explain like a relatively philosophical point about how to set up the development process if you're in such a context, basically. I will give you the link directly because I don't have time for the. Okay, this is something we wrote together with the main self-driving software guys at Starship. The core idea is that you, instead of trying to do that kind of thing where you want to build a self-driving robot, you want the main problem there were too many accidents, or the safety of the robot, which is defined as how often a dangerous situation happens. It was too bad, like 200x or something too bad. And in that situation, the question is, well, there's no question. Like it's just hopeless. You don't even ask questions. Then when someone does ask a question, in that case it was I wasn't there, but the CTO was kind of pushing the computer vision lead to the direction of basically take the list of cases that went wrong. Take the instances where the behavior was dangerous. Take the easiest, so try to understand what is going on roughly, and take the 50% easiest cases and solve them. And you only have to repeat that 8 times to get 250x better. So to answer your question, I guess if you're in a situation like that, where Starship, that took Starship 3 years to do that 200x. This kind of development process you can't really do in a sprint cycle, like 1 or 2 weeks. So one part, I guess, is managing expectations. The other part, once you do relatively standard things like training image classification model, like this is basically the most standard neural network I think there is. Once you have done that once or twice, you have a rough idea of how much data you need. You probably use a standard neural network for this. You don't change the architecture. So it's mostly about the data collection and iterating the data until you have the right data set. And that you can relatively easily predict, because there's, like humans have some throughput in how quickly they annotate data, and you can basically make this calculation. In the general case of, like, here is this cool machine learning task, how long will it take? I mean, I don't believe, it's kind of trying to predict things which have never been done, from 0 data points. You kind of get where I'm getting, right? It's difficult, yeah. Sorry for no answer.
Can you put machine learning into estimation?
Can you put machine learning into
estimation?
Estimation?
How much time it will take?
Oh, okay. So specific things you can potentially, like I said, I think it would be relatively easy for us to estimate building something similar to the document classification model that we have in production. Like this we can do. Again, in the general case of machine learning, it depends on what you're trying to do. If you're trying to, based on my smartphone image, or if I take a photo here with my phone, based on this, trying to detect the humans in the far windows of that house over there, I think it is in principle possible. Like the pixels exist, the bits exist, but it's difficult to tell how accurate it will be. And I guess also one point about estimation is, I can give you an immediate. I could literally write the Python code for you right now, for a classifier if you don't specify what the accuracy has to be. So if you give me the like the performance requirements, that actually only specifies the task already, and also the data then, which if these are trivial examples of the cats I showed, then it's much easier than the more complex cases.
So I forgot to say previously that Taivo will have a chance to give out 3 T-shirts by his own choice, and usually those go to those who ask questions. But since we don't have more time for questions, then okay, one more question. So Taivo will have to choose 3 from 4.
But then I will have to pick the one who had the worst question. Maybe we finish now and give everyone a T-shirt.
Okay, let's finish now. Let's have a break. Please don't spill out any drinks. Let's do break like for 10-15 minutes. Those who are next to window, please open windows. And chocolate and socks to Taivo. Thank you.
Thank you.